Okay, so before we move on to the next part of our notes, I just want to show you a couple of examples similar to what you might have on your homework tonight. So you might have a drawing similar to the one that's given here for our angle addition postulate, and you might be given the fact that the distance between A and Z is given to you to be x plus 3, and maybe Z to be is x minus 2. And then you may be told that from A to B is 11 units, and you might be asked to solve for x. And so using the angle, or the segment addition postulate, remember the parts add up to be the whole. And so to start off, you would set up the equation, the parts, which are x plus 3 and x minus 2, add, so I'm going to plus between there, to equal the whole, which is 11. And so this is the way that your equation would look. X plus 3 plus x minus 2 equals 11. So then it's just algebra from there on. You're combining your like terms of the x's and the 3 and the negative 2, and then using your subtraction property of equality and then your division property of equality to get your value of x to be 5. You can always check your answer by putting that back in for x into the two expressions. That would make a to z be 8 and z to b be 3, and 8 plus 3 does equal to be 11. So same thing with your angle addition postulate. You may be given these amounts and asked to find the other ones. So for example, you might be given that angle AXB is 20 degrees, and you may be told that AXD, the whole thing, is 80 degrees, and then asked what is the measure of angle BXD. Well, if this is the whole and this is one of the parts, to find the other part, you would simply do 80 minus 20, so that missing angle would have to be 60 degrees. So that's just similar to some problems that you'll have on your homework tonight. All right, so moving along to the next part in your notes, we're going to be looking at an application of the angle addition postulate. So it says, here's an application of the angle addition postulate. In the diagram, angle AXD is a straight angle. And we know that because points A, X, and D are what we call collinear points, meaning they're on the same line. So they make a straight angle together. We also see in the picture that point B is on the interior of that angle. It's inside of it. And so we're going to look at answering these questions to see a special relationship between these angles in this diagram. So part A says, given that angle AXD is a straight angle, what do we know about its measure? Well, we already know that a straight angle has 180 degrees. Now, how do we know that? Because in proofs, we're going to always have to justify our answer. And so the reason why we know straight angles are 180 degrees is because of the definition of what a straight angle is. So that's the definition of a straight angle. So if you were to look up the definition of a straight angle is an angle whose measure is 180 degrees. So by definition, we know that. Part B says, because we know that point B is in the interior of angle AXD, what does the angle addition postulate tell us about these angles? So we just learned the angle addition postulate, and remember, anytime you hear the words addition postulate, I want you to always think parts add up to be the whole. And so what do we know based on the angle addition postulates? We know these two parts add up to be the whole. And so we're going to write that down in a specific way. We're going to write the measure of angle AXB, which is the first part, plus the measure of angle BXD, which is our second part in the diagram, is equal to the measure of the whole, which is the measure of angle AXD. And again, why do we know that to be true? Because of the angle addition postulate. So part C says, now that we know two things that are both equal to the measure of angle AXD, so I'm going to go back to A and I'm going to write the measure of angle AXD equals 180 degrees because that's what we were saying. So you can see what we mean by part C. We have the measure of angle AXD equal to this, and we have the measure of angle AXD equal to this. So we have two things equal to the measure of angle AXD. So we can use the transitive property from the front of our notes, which remember just says if A equals B and B equals C, then A equals C. So anytime you know two things are equal to the same thing, you can set them equal to each other. So since we have both of these equal to the measure of angle AXD, we can set them equal to each other. So we're going to write the measure of angle AXB plus the measure of angle BXD from part B is equal to 180 degrees from part A. And again, that's the transitive property that allows us to do that. Part D, what do we call angles whose measures sum to 180? Well, I'd like you to add a little something here to that statement. Really, it's what do you call two angles whose sum measures to 180 degrees. So remember, those are called supplementary angles. Two angles that have a sum of 180 degrees are called supplementary angles. And which two angles have this property? Well, we just said that the measure of angle AXB plus the measure of angle BXD add to 180. So angles AXB and angle BXD have that property. So a theorem is a new word for us, is a statement that has been proven to be true for all cases. And we just proved a theorem when we just stated that these are supplementary angles. So angles AXB and BXD have a special word for them. They are called a linear pair. And so you have heard of linear equations before, so anytime you see the word linear, you're thinking line, and of course you know what a pair is. A pair is two of something. And so a linear pair is just simply two angles. They have to be adjacent to each other, which means they have to be next door to each other and share a side. And they have to form a straight angle together. So any two angles that form a straight angle together are called a linear pair. So angle AXB and BXD are a linear pair because they're adjacent to each other, they share this side, and they make a straight angle together. So using what we just learned in the previous questions, we're going to write a theorem about linear pairs. So since we know AXB and BXD are a linear pair, and what did we learn about them? We learned that they are supplementary angles. We're going to write that together to make what's called the linear pair theorem. So this is the linear pair theorem. It's been proven. We just did an informal proof of it in number 6. So linear pair theorem states that linear pair are supplementary. It's that short and easy. The linear pair theorem simply states that if you have a linear pair, you know they're supplementary to each other. So we have to know what supplementary means. In order to apply that, we have to know that that means they add to be 180 degrees. So in number 9, we are going to start looking at proofs here. And this is a flowchart proof, and you can kind of see the flowchart reason it's called that and the appearance of it. And we have several choices here that we're going to be using for the reasons for each one of these statements. So anytime you have a proof, you're going to be given a statement and being asked to prove something. So typically the given part will show up at the beginning of your proof, but not always, but most of the time it is. And then the proof will always be your last statement. So you can see what we're trying to prove is LA equals IN, and you see that as the very last statement in our proof. And so when you are given something, then in your proof, when you state it, you simply use the reason given as your statement, or as your reason for the statement. So here we're given LI equals AN, and that's the very first thing in our proof. And so there's that statement, and our reason is simply given. And it's the only thing that's given, so I'm going to go ahead and mark that out as a choice. I'm definitely not going to be using that again because there was nothing else given in here. So we are given that LI, from here, L to I, is the same distance as AN, A to N. That was the given statement. Now, these two statements are from a postulate that we learned today. LA plus AI equals LI. LA plus AI equals LI. Again, those are parts adding to equal the whole, and that's always an addition postulate, and since these are segments, that's called the segment addition postulate. Likewise, this is exactly the same thing. AI plus IN equals AN. The parts add to the whole. Again, this is segment addition postulate. So we're using that reason twice, and that's certainly allowed. These are both using that postulate. So if you can see these little lines on the flow chart proof that we're doing, it's saying that these three statements are being used together to form this one right here. And we're kind of doing similar to what we did on part C of number 6. Since we have the fact that LI and AN are equal, anything that's equal to LI, I can replace in this part of this equation. And AN, anything I know to be equal to that, I can replace AN with that. So since I know LI is equal to the sum of these parts, I can replace LI in my given statement with LA plus AI. Here that is right here. And with AN, since I know AN is equal to AI plus IN, I can replace AN in this equation with AI plus IN. So we simply substituted into this equation things that we knew to be equal to them. So that is using the substitution property. Replacing something with what you know to be equal to it. And so now, if you'll notice in this equation, we have AI on both sides of the equation. So when you have something on both sides of your equation, what algebraically allows you to get rid of that? Well, we can subtract it away. So we didn't show this step in our proof, but what we're doing is we're subtracting AI from both sides of the equation, making that AI go away and leaving us with LA equal to LN. And so the reason that we're able to get to this step is using the subtraction property of equality. And again, we can just call it subtraction property. You'll probably not want to use SUB for subtraction and substitution. It's kind of unclear what I mean there. So I'm going to add a little TR there just so I know that I'm talking about subtraction property and not substitution property. So I spelt out substitution. I could have spelt out subtraction. I was just being lazy. So I'll use SUBTR for that. So that's your very first geometric proof. Let's look at another on the back of your notes. So this is very similar to the one that we just did. This one is in a different form. This is called a two-column proof for obvious reasons. You have a column that's your statements and a column that's your reasons. Very similar to the one before because we're using the same picture, but we're given different information. We're asked to prove the exact same thing. So remember, typically your given is at the beginning of your proof, as it is in ours. The reason for this statement is given. So for my statement, I'm simply going to write LA equals IN. Now remember, the very last step in your proof is an easy one as well, because you know you have to have here what you're trying to prove. So I know my very last statement better be LI equal to AN. That's what I'm working towards in my proof, is proving that that is true. So we have here the addition property of equality. So remember, we learned that at the front of our notes. That just simply means we can add the same thing to both sides of an equation. So we're going to be adding something to LA and adding the same thing to IN. So looking at your choices up here, the only one that has addition is right here. And they did. They added AI to both sides of the equation. So that's our statement here. We're taking the LA from number 1 and adding AI to it, and the IN from number 1 and adding AI to it. That's the addition property of equality that allows you to add the same thing to both sides of an equation. The next two are segment addition postulates. Remember, those are parts adding to equal the whole. Now the addition part is already given here for us, so what are we adding to LA? Well, LA is this part. The part next to it is AI, and those two parts together make LI. So I'm going to write LA plus AI equals the whole thing, which is L to I. So you can see that AI equals